Dear students, today's topic is potential formulation U for U and A, that is A vector, that is the magnetic vector potential. This is the electric scalar potential and this is magnetic vector potential. At the relativistic fields, when we have or the relativistic levels, when the things are moving with the near to the speed of light. So the topic code is EMPF-S1. This is electromagnetic potential formulation -S1. In electrostatics, curl of E is equal to 0. This expression allowed us to write E as a gradient of a scalar potential, that is E is equal to minus gradient of U. In electrodynamics, this is no longer possible because the curl of E is non-zero, but B remains divergenceless, so we can still write B is equal to curl of A. As in magnetostatics, putting it into the Faraday law field, we get the curl of E is equal to minus delta B by delta T, which is equal to minus, putting the B value here, the minus delta by delta T curl of A. The curl of further rearranging this expression, and curl of E plus space time, we are here in this case we are taking independent at the moment, so curl of E and the T, the only thing which we are looking for, the variation is taking place in A, magnetic vector potential, which is the main the field at the moment is being affected by this transformation. So curl of E plus curl of delta A by delta T is equal to 0. Curl of the E plus delta A by delta T is equal to 0. Hence, here is a quantity unlike E alone, whose curl does not vanish. It can be written as the gradient of a scalar potential. So E plus delta A by delta T is equal to minus gradient of U. Hence E is equal to minus gradient of U minus delta A by delta T dash 2. This is equation 2. This is equation number 2. This reduces the above equation 2 to old form, of course, in electrostatics, as we put delta A by delta T is equal to 0. But at a classical level, that is delta A by delta T is equal to 0. Non-relativistic level, this delta A by delta T is equal to 0. So we are then reduced or confined to this old equation E is equal to minus gradient of U. Now the potential formulation of equation 1 and 2 automatically fulfills the two homogeneous magnetic equations, that is the divergence of B is equal to 0 and curl of E is equal to minus delta B by delta T. But what about the Gauss's law in electrostatics and Ampere's law with Maxwell equation? That is the Gauss's law is given as divergence of E is equal to rho by epsilon naught, and this is the Faraday law, the Ampere's law. The curl of B, Ampere's law, curl of B is equal to mu naught J plus mu naught delta D by delta T for free space. So putting the equation 2, the E value in Gauss's law, putting this equation, the value of E, the law for the Gauss's law for electrostatics now take. Here we have if you look back, the divergence, the Poisson equation takes now the new form by putting the relevant term of the E electric field, which is minus divergence minus gradient of U minus delta A by delta T is equal to rho by epsilon naught. So putting that here, we will get del square of U, the gradient, we put a del operation on the gradient, then it will give you del square of U, and the divergence of A we take inside, and delta by delta T of the divergence by delta T. And remember, it is again for free space, putting B is equal to curl of A, E is equal to minus gradient of U minus delta A by delta T, what we get that the curl of A is equal to mu naught J minus mu naught epsilon naught gradient of delta U by delta T minus epsilon naught mu naught delta 2A by delta T square. Just we have replaced the values here, E value this one, and here the B the U, which is the, in this case, gradient of U. E value is now minus gradient of U, which is now delta. We have taken the operator which is the outside delta by delta T. So we have just replaced the value of E over here, and we have got the using the vector identity here, what we get, curl of A is equal to the gradient of the divergence of A minus del square of A. This is question number 4. Now we have the putting that in the above equation, we have now the rearranging it. We have got the del square of A minus mu naught epsilon naught mu naught delta 2 A by delta T square minus the gradient of the divergence of A plus mu naught epsilon naught delta U by delta T is equal to minus mu naught J. Equation number 5. Now equation 3 and 5 carry all the information. This equation 5 is now carry all the information in electrodynamics for the potential formulation that we have now for the formulated the potential. This is magnetic. This is for the magnetic vector potential has to be dealt with these terms. The divergence of A must be there, the delta U by delta T must be there, the sum of these two, and the gradient of the sum of these two, gradient of the sum of the divergence and the rate of change of the U. So that's how we transform or the formulated the potentials U and A from classical to the electrodynamics are at the relativistic levels when the things are relativistics. So the equation 3, which was less of this formulation. Okay, dear students, with this we reach to the end of the topic. See you next time, inshallah, with a new topic. Till then, thank you.